This is our demo platform with the VPN Concentrator sitting at the edge of the enterprise headquarters. Remote workers and enterprise subsidiary sites open IPSec tunnels towards the VPN Concentrator for a secure connection to the enterprise resources. The VPN Concentrator is composed of two Turbo IPSec instances working in high availability mode, with VRP for redundancy and Ixia for seamless failover, thanks to the continuous synchronization of IPSec security policies and associations. The cluster is monitored using the Grafana visualization tool. We run each vRouter instance on 5 cores, 10 threads of a dual socket platform equipped with Intel Xeon Platinum 8170 CPUs running at 2.10 GHz. Each instance is allocated 8 GB of RAM. We use an Ixia XM2 traffic generator to inject traffic at high rate, and we emulate up to 10K remote IPSec connections thanks to StrongSwan's load tester tool running on a separate platform. Let's start our demo by reviewing the VPN concentrator configuration using the CLI on the first VPN concentrator called VPN C1. Using the show config command, we start by reviewing system information. We see the host name vpnc1.vpnc.6win.com and the dimensioning of the vRouters high-performance packet processing engine called the fastpath. We see that 2 NICs and 4 cores 8 threads are assigned to the fastpath for this test. Then we can dump the interfaces. This shows a management interface, one interface to the LAN, one interface to the WAN, one interface for high availability synchronization, and the VRP's interfaces used for redundancy. With this configuration, we will be able to demonstrate up to 10 gigabit per second of traffic in both directions, or in other words, 20 gigabit per second of IPSec processing. Now, let's check the routing configuration. In this case, it is very simple, with static routes configured to send clear flows towards the Ixia. Next comes the IPSec configuration itself. We can see the general options, tuning the capacity of the IPSec stack. We can see the VPN configured with security policies for the Ixia for throughput and with the load tester tool for tunnel establishment, as well as the pre-shared key used to authenticate IK exchanges. The configuration of this VPN relies on templates that define the parameters of the IKE phase 1 and phase 2 negotiations, including Diffie-Hellman group, encryption and authentication algorithms, rekey time, replay window size, and more. In this test, we use AES GCM with a key size of 128 bits for the IPSec ESP encryption. We can check the equivalent configuration in XML format on the second VPN concentrator used for high availability. This is what a netconf client would send to the vRouter to configure it in a programmatic way. We see the same information, including routes, interfaces, IKE templates, VPN and security policies, etc. Back on VPN C1, let's check the status of the interfaces. We see that the IP addresses are properly configured, including the VRP interfaces, meaning that VPN C1 is the master for the high availability cluster. Let's now switch to the Ixia traffic generator. This is the IX network UI, where we can see the different flows. There are 8 flows configured in each direction using two 10 gig ports. The throughput indicated by the Ixia gauges is for clear traffic. When encapsulated with IPSec, the packet size and therefore the throughput increase. With the algorithms used in this demo, 20 gigabit per second of IPSec traffic correspond to 18.9 gigabit per second of clear traffic throughput. Let's start the traffic. We see that 18.906 gigabit per second of clear traffic can be processed without any packet loss, which means that we achieve 20 gigabit per second of IPSec processing. While the traffic is running, we can dump the packets on VPN C1 to verify that they are encrypted using ESP. Let's now have a look at the key performance indicators in the CLI. These KPIs include product information such as license and version, system information such as CPU or memory usage, networking statistics, and others. These are streamed from the vRouter to an InfluxDB time series database and then displayed in the Grafana Analytics dashboard to better analyze the dynamics of the system. In the dashboard for VPN C1, we see the status of the system, including CPU usage in Linux and in the vRouter's fastpath. We see that we reach the link capacity for the WAN interface when IPSec packets flow. And a bit down the screen, the IPSec SA and SP graphs reflect the 16 security policies and associations used to protect the Ixia traffic. Scrolling through the dashboard, we can also see process usage, user count, and disk usage. Let's now check the IPSec state in detail using the CLI. We can dump all IKE VPNs to review their status and the corresponding peers' IP addresses and fully qualified domain names. The total number of VPNs can also be displayed. When needed, we can filter the output on a specific peer for debug purposes. The detailed output includes the states of the security associations, the local and remote endpoints, the lifetime of the security associations, statistics in bytes and packets, and more. Finally, the show log command allows to review the sequence of IKE events, and it can be filtered out for a specific peer. Let's now demonstrate tunnel establishment rate. Our screen is split between the CLI on VPN C1 on the top and the load tester command line on the bottom. Load tester is a tool from the StrongSwan open source project that can simulate the connections of IPSec clients at high rate. The VPN count on VPN C1 is 8 when we start the load tester tool. As connections start establishing, we can see the VPN count increase on VPN C1. In Grafana, the IPSec Security Association and Security Policy graphs show us the IPSec connections being established until 20K SAs and SPs are reached, which corresponds to our objective of 10K IPSec tunnels. We see on the graph that the Ixia traffic is still going through at wire speed. So we have just demonstrated that we can maximize the capacity of a full duplex 10 gigabit per second link with IPSec traffic, while establishing up to 10K tunnels. Let's now check high availability. This is another Grafana dashboard where we see a high-level status of the redundant instances of the VPN concentrator. Both are active and in good shape. We can see from the fastpath CPU usage graph that VPN C1 is the active instance processing the IPSec traffic. fastpass CPUs are inactive on VPN-C2, but we will see that the IKE sessions are synchronized and VPN-C2 is ready to take over traffic in case VPN-C1 fails. Our screen is split between CLI consoles on VPN-C1 on the left and VPN-C2 on the right. The VRP configuration and state show that VPN-C1 is the VRP master and VPN-C2 is the backup. The VRP interfaces on VPN-C1 bear the virtual IP addresses of the cluster, while there are no IP addresses on the VRP interfaces on VPN-C2. Now that we have reviewed link redundancy, let's check IKE sessions. The high availability configuration shows the group, the synchronization interface, and the peers addresses that are used to continuously synchronize the IKE sessions between the active and inactive systems. We see the 10K plus 8 IKE VPNs configured on both sides. These have been synchronized on VPN-C2 while they were established using load tester on VPN-C1. We will now trigger an activity switch by setting down the interface connected to the LAN interface of VPN-C1. This will cause VRP to change states and VPN-C2 to take over traffic. We can see from the CLI that VPN-C1 is now backup and VPN-C2 has become master. The virtual IPs of the VRP cluster are now configured on VPN-C2 for both LAN and WAN interfaces. Back to the Grafana overview dashboard, VPN-C2's fastpass CPUs are now loaded, indicating that IPSec processing has been taken over. On the other hand, fastpass CPU usage on VPN-C1 is 0. Looking at the detailed dashboard on VPN-C1, it is now clear that traffic is not being processed as the throughput of the interfaces is 0. On VPN-C2, on the other hand, the throughput is 20 gigabit per second, meaning that traffic has properly been taken over thanks to the already established VPNs when the activity switch occurred. This concludes our demo, where we have demonstrated how 6WIN's vRouter can be deployed on a standard off-the-shelf server as a VPN concentrator to terminate 10K IPSec tunnels, maximizing throughput on a 10 gigabit per second link and providing redundancy and seamless failover, all this being monitored in a graphical environment. In our demo, we used 5 cores per VPN concentrator instance and 8 gigabytes of RAM, knowing that throughput scales with the number of cores and the number of tunnels scales with memory.